You said, chemical bonds. ChatGPT said. Here is your CSIR Net JRF Life Sciences detailed lecture on Unit, molecules and their interaction relevant to biology. Topic C, chemical bonds and forces that stabilize biomolecules. Chemical bonds and intermolecular forces form the backbone of molecular interactions in biological systems. Understanding these interactions is critical to interpreting how molecules acquire structure, stability, and function inside the cell. These bonds not only determine molecular formation but also mediate protein folding, DNA stability, enzyme-substrate interaction, cell membrane architecture, and signal transduction. At the core are strong covalent bonds, which form when atoms share electrons to complete their valence shells. Covalent bonds are the primary bonds that link atoms within biomolecules. For instance, peptide bonds link amino acids in proteins, and phosphodiester bonds connect nucleotides in DNA and RNA. These bonds have high bond energies, typically 80 to 100 kcal per mole, making them stable under physiological conditions. Ionic bonds, electrostatic interactions, occur between atoms with opposite charges, such as between a cation, e.g., Na, and an anion, e.g., Cl. In biological macromolecules, ionic bonds form between charged side chains of amino acids, like lysine positive and glutamate negative, and are particularly strong in hydrophobic environments like protein interiors. However, in aqueous environments, their strength decreases due to solvation by water molecules and the high dielectric constant of water. Hydrogen bonds are vital in stabilizing secondary and tertiary structures of proteins and the double helical structure of DNA. These bonds form when a hydrogen atom covalently bonded to an electronegative atom, like N or O, interacts with another electronegative atom. Though individually weak, approximately 1 to 5 kcal per mole, their directionality and multiplicity make them powerful when collectively present. For example, the Watson-Crick base pairing in DNA is held together by specific hydrogen bonds, AT with 2, GC with 3. Van der Waals forces are weak interactions caused by transient dipole moments when electron clouds of two non-bonded atoms fluctuate and induce mutual polarization. These forces play an essential role in molecular packing, such as in the hydrophobic cores of proteins, where atoms are packed tightly for stability. Though individually feeble, collectively they contribute significantly to protein folding and molecular recognition. Hydrophobic interactions are not true bonds but entropically driven forces where nonpolar molecules or parts of molecules aggregate to exclude water molecules. This is crucial in the formation of lipid bilayers, membrane proteins, and protein folding, where nonpolar side chains collapse into the protein's interior to minimize exposure to aqueous surroundings. These interactions are strengthened by the entropy gain from releasing ordered water molecules that otherwise form cages around nonpolar surfaces. Disulfide bonds, formed by the oxidation of two cysteine residues, are covalent but unique to proteins, especially extracellular ones. These stabilize tertiary and quaternary structures, particularly in secreted proteins, antibodies, and insulin. All these forces collectively determine the conformation and stability of biomolecules. For example, in proteins, the alpha helix and beta sheet structures are stabilized by hydrogen bonds, while the overall 3D shape arises from a combination of hydrogen bonding, hydrophobic interactions, van der Waals forces, ionic interactions, and occasionally disulfide bridges. The specificity and reversibility of weak interactions make them ideal for dynamic biological processes such as enzyme-substrate binding, antigen-antibody recognition, and hormone-receptor interactions, where transient binding and unbinding are essential. In DNA-protein interactions, such as in transcription factors binding to promoter regions, electrostatic attraction, hydrogen bonding, and shape complementarity all contribute to specificity. Similarly, in signal transduction, ligand binding to receptors involves multiple weak bonds to ensure reversible, regulated interactions. In conclusion, while covalent bonds provide stability and permanence in molecular structures, non-covalent interactions provide the flexibility, specificity, and dynamic behavior necessary for life. The cooperative action of these forces ensures that biomolecules are stable yet adaptable, a balance that is crucial for biological function. Previous year questions, PYQs, with answers 1. CSIR Net June 2016. Hydrophobic interactions are primarily driven by a formation of hydrogen bonds between hydrophobic groups. B. Dipole-dipole attraction. C. Entropy-driven exclusion of water. D. Covalent bonding between hydrophobic groups. Answer. C. Entropy-driven exclusion of water. 2. CSIR Net Deck 2019. Which of the following bonds interactions is strongest under physiological conditions? A. Hydrogen bond. B. Ionic bond. C. Van der Waals interaction. D. Covalent bond. Answer. D. Covalent bond. 3. CSIR Net June 2014. In the alpha helix structure of proteins, which type of bond stabilizes the helical turn? A. Ionic bond. B. Disulfide bond. C. Hydrogen bond. D. Peptide bond. Answer. C. Hydrogen bond. Would you like me to continue with the next topic, such as composition, structure and function of biomolecules, or move to another unit like cell biology or gene expression? You said. Composition, structure and function of biomolecules. Carbohydrates. ChatGPT said. Here is your CSIR Net JRF Life Sciences high quality lecture on Unit, molecules and their interaction relevant to biology. Topic D. Composition, structure and function of biomolecules. Carbohydrates. Carbohydrates are one of the primary classes of biomolecules that serve as energy sources, structural materials, and recognition molecules in biological systems. Chemically, carbohydrates are defined as polyhydroxyaldehydes or ketones and their derivatives. They are composed of carbon C, hydrogen H, and oxygen O, usually in the empirical formula CHON. Their structural diversity arises from variations in chain length, functional groups, glycosidic linkages, and branching patterns. Carbohydrates are classified into three main types. Monosaccharides, simple sugars, e.g., glucose, fructose, galactose. Oligosaccharides, short chains of monosaccharide units, e.g., sucrose, lactose. Polysaccharides, long chains of monosaccharides, e.g., starch, glycogen, cellulose. 1. Fat-soluble vitamins. These are stored in the liver and adipose tissues and do not need to be consumed daily. They are absorbed along with dietary lipids and transported via chylomicrons. Vitamin A, retinoids, and carotenoids. Functions: vision as retinal, gene expression, immune function, and epithelial integrity. Sources: liver, dairy products, and carotene-rich vegetables. Deficiency: night blindness, xerophthalmia, keratomalacia. Mechanism: retinoic acid acts as a transcription factor, regulating gene expression involved in cell differentiation. Vitamin D, calciferol. Functions: regulates calcium and phosphate homeostasis, bone mineralization. Sources: synthesized in skin upon UV exposure, fish liver oils, dairy. Deficiency: rickets in children, osteomalacia in adults. Mechanism: acts through nuclear vitamin D receptors to modulate transcription of calcium-transporting proteins. Vitamin E, tocopherols and tocotrienols. Functions: antioxidant, protects membrane lipids from oxidative damage. Sources: vegetable oils, nuts, seeds. Deficiency: hemolytic anemia in newborns, neurological symptoms. Mechanism: scavenges free radicals, preventing peroxidation of polyunsaturated fatty acids. Vitamin K, phylloquinone and menaquinone. Functions: coenzyme for gamma-glutamyl carboxylation of clotting factors 2, 7, X, and X. Sources: green leafy vegetables, gut microbiota synthesis. Deficiency: hemorrhagic disorders, easy bruising. Mechanism, essential for post-translational modification of blood coagulation proteins. 2. Water-soluble vitamins. These are not stored significantly in the body and require regular dietary intake. They generally function as coenzymes in various metabolic pathways. Vitamin B1 thiamine. Coenzyme form, thiamine pyrophosphate TPP. Functions, carbohydrate metabolism, oxidative decarboxylation of alpha-keto acids. Deficiency, beriberi, Wernicke-Korsakoff syndrome, especially in alcoholism. Enzymes, pyruvate dehydrogenase, alpha-ketoglutarate dehydrogenase, transcriptase. Vitamin B2 riboflavin. Coenzymes, FMN and FAD. Functions, redox reactions in electron transport and oxidative metabolism. Deficiency, angular stomatitis, chylosis, glossitis. Enzymes, succinate dehydrogenase, acyl-CoA dehydrogenase. Vitamin B3, niacin. Coenzymes, NAD+, NADP+. Functions, redox reactions, energy metabolism. Deficiency, pellagra 4Ds, diarrhea, dermatitis, dementia, death. Can be synthesized from tryptophan. Vitamin B5 pantothenic acid. Vitamin B1 thiamine. Coenzyme form, thiamine pyrophosphate TPP. Functions, carbohydrate metabolism, oxidative decarboxylation of alpha-keto acids. Deficiency, beriberi, Wernicke-Korsakoff syndrome, especially in alcoholism. Enzymes, pyruvate dehydrogenase, alpha-ketoglutarate dehydrogenase, transcriptase. Vitamin B2 riboflavin. Coenzymes, FMN and FAD. Functions, redox reactions in electron transport and oxidative metabolism. Deficiency, angular stomatitis, chylosis, glossitis. Enzymes, succinate dehydrogenase, acyl-CoA dehydrogenase. Vitamin B3, niacin. Coenzymes, NAD+, NADP+. Functions, redox reactions, energy metabolism. Deficiency, pellagra 4Ds, diarrhea, dermatitis, dementia, death. Can be synthesized from tryptophan. Vitamin B5 pantothenic acid. Component of coenzyme A. Functions, acyl group transfer reactions, fatty acid metabolism. Deficiency, rare, may cause fatigue, GI symptoms, paresthesia. Vitamin B6 pyridoxine, pyridoxal, pyridoxamine. Coenzyme, pyridoxal phosphate, PLP. Functions, transamination, decarboxylation, neurotransmitter synthesis. Deficiency, convulsions, peripheral neuropathy. Enzymes, aminotransferases ALT, ASP glutamate decarboxylase. Vitamin B7 biotin. Coenzyme for carboxylase enzymes. Functions, fatty acid synthesis, gluconeogenesis. Deficiency, dermatitis, alopecia, caused by raw egg white avidin binds biotin. Vitamin B9 folate. Coenzyme, tetrahydrofolate THF. Functions, 1 carbon transfer in DNA, RNA synthesis. Deficiency, megaloblastic anemia, neural tube defects in fetus. Antagonists, methotrexate inhibits DHFR, blocking THF formation. Vitamin B12 cobalamin. Functions, DNA synthesis, fatty acid and amino acid metabolism. Coenzymes, methylcobalamin, 5-'deoxyadenosylcobalamin. Deficiency, pernicious anemia, neuropathy, methylmalonic acidemia. Needs intrinsic factor for absorption in ileum. Vitamin C, ascorbic acid. Functions, antioxidant, collagen synthesis, iron absorption. Deficiency, scurvy, bleeding gums, joint pain. Mechanism, cofactor for proline and lysine hydroxylation in collagen synthesis. Role of vitamins in enzyme catalysis. Many vitamins act as precursors for coenzymes and prosthetic groups essential for the catalytic activity of enzymes. Deficiency of these vitamins impairs the function of specific enzymes, which manifests in clinical symptoms and metabolic disorders. Clinical and biotechnological applications. 1. Fat-soluble vitamins. These are stored in the liver and adipose tissues and do not need to be consumed daily. They are absorbed along with dietary lipids and transported via chylomicrons. Vitamin A, retinoids and carotenoids. Functions, vision as retinal, gene expression, immune function, and epithelial integrity. Sources, liver, dairy products, and carotene-rich vegetables. Deficiency, night blindness, xerophthalmia, keratomalacia. Mechanism, retinoic acid acts as a transcription factor, regulating gene expression involved in cell differentiation. Vitamin D, calciferol. Functions, regulates calcium and phosphate homeostasis, bone mineralization. Sources, synthesized in skin upon UV exposure, fish liver oils, dairy. Deficiency, rickets in children, osteomalacia in adults. Mechanism, acts through nuclear vitamin D receptors to modulate transcription of calcium-transporting proteins. Vitamin E, tocopherols and tocotrienols. Functions, antioxidant, protects membrane lipids from oxidative damage. Sources, vegetable oils, nuts, seeds. Deficiency, hemolytic anemia in newborns, neurological symptoms. Mechanism, scavenges free radicals, preventing peroxidation of polyunsaturated fatty acids. Vitamin K, phylloquinone and menaquinone. Functions, coenzyme for gamma-glutamyl carboxylation of clotting factors 2, 7, X, and X. Sources, green leafy vegetables, gut microbiota synthesis. Deficiency, hemorrhagic disorders, easy bruising. Mechanism, essential for post-translational modification of blood coagulation proteins. 2. Water-soluble vitamins. These are not stored significantly in the body and require regular dietary intake. They generally function as coenzymes in various metabolic pathways. Vitamin B1 thiamine. Coenzyme form, thiamine pyrophosphate TPP. Functions, carbohydrate metabolism, oxidative decarboxylation of alpha-keto acids. Deficiency, beriberi, Wernicke-Korsakoff syndrome, especially in alcoholism. Enzymes, pyruvate dehydrogenase, alpha-ketoglutarate dehydrogenase, transcriptase. Vitamin B2 riboflavin. Coenzymes, FMN and FAD. Functions, redox reactions in electron transport and oxidative metabolism. Deficiency, angular stomatitis, chylosis, glossitis. Enzymes, succinate dehydrogenase, acyl-CoA dehydrogenase. Vitamin B3, niacin. Coenzymes, NAD+, NADP+. Functions, redox reactions, energy metabolism. Deficiency, pellagra 4Ds, diarrhea, dermatitis, dementia, death. Can be synthesized from tryptophan. Vitamin B5 pantothenic acid. Component of coenzyme A. Functions, acyl group transfer reactions, fatty acid metabolism. Deficiency, rare, may cause fatigue, GI symptoms, paresthesia. Vitamin B6 pyridoxine, pyridoxal, pyridoxamine. Coenzyme, pyridoxal phosphate, PLP. Functions, transamination, decarboxylation, neurotransmitter synthesis. Deficiency, convulsions, peripheral neuropathy. Enzymes, aminotransferases ALT, AST glutamate decarboxylase. Vitamin B7 biotin. Coenzyme for carboxylase enzymes. Functions, fatty acid synthesis, gluconeogenesis. Deficiency, dermatitis, alopecia, caused by raw egg white avidin binds biotin. Vitamin B9 folate. Coenzyme, tetrahydrofolate THF. Functions, 1-carbon transfer in DNA, RNA synthesis. Deficiency, megaloblastic anemia, neural tube defects in fetus. Antagonists, methotrexate inhibits DHFR, blocking THF formation. Vitamin B12 cobalamin. Functions, DNA synthesis, fatty acid and amino acid metabolism. Coenzymes, methylcobalamin, 5-'deoxyadenosylcobalamin. Deficiency, pernicious anemia, neuropathy, methylmalonic acidemia. Needs intrinsic factor for absorption in ileum. Vitamin C, ascorbic acid. Functions, antioxidant, collagen synthesis, iron absorption. Deficiency, scurvy, bleeding gums, joint pain. Mechanism, cofactor for proline and lysine hydroxylation in collagen synthesis. Role of vitamins in enzyme catalysis. Many vitamins act as precursors for coenzymes and prosthetic groups essential for the catalytic activity of enzymes. Deficiency of these vitamins impairs the function of specific enzymes, which manifests in clinical symptoms and metabolic disorders. Clinical and biotechnological applications, vitamin-based supplementation in metabolic disorders. Diagnostic biomarkers for deficiencies, e.g., methylmalonic acid for B12. Folate antagonists, e.g., methotrexate used in chemotherapy. Vitamin C and antioxidant therapy and wound healing. Previous year questions, PYQs with answers 1. CSIR Net Deck 2013. Which one of the following vitamins acts as a coenzyme in carboxylation reactions? A biotin. B-thiamine C, riboflavin D, niacin. Answer, a biotin. Biotin is a coenzyme for carboxylases like pyruvate carboxylase and acetyl-CoA carboxylase. 2. CSIR Net June 2015. A deficiency of which vitamin causes megaloblastic anemia? A vitamin B1. B, vitamin B9 C, vitamin B6 D, vitamin C. Answer, B, vitamin B9. Folate is essential for nucleotide synthesis. Its deficiency leads to impaired DNA replication and anemia. Vitamin A, retinoids and carotenoids. Functions, vision as retinol, gene expression, immune function, and epithelial integrity. Sources, liver, dairy products, and carotene-rich vegetables. Deficiency, night blindness, xerophthalmia, keratomalacia. Mechanism, retinoic acid acts as a transcription factor, regulating gene expression involved in cell differentiation. Vitamin D, calciferol. Functions, regulates calcium and phosphate homeostasis, bone mineralization. Sources, synthesized in skin upon UV exposure, fish liver oils, dairy. Deficiency, rickets in children, osteomalacia in adults. Mechanism, acts through nuclear vitamin D receptors to modulate transcription of calcium-transporting proteins. Vitamin E, tocopherols and tocotrienols. Functions, antioxidant, protects membrane lipids from oxidative damage. Sources, vegetable oils, nuts, seeds. Deficiency, hemolytic anemia in newborns, neurological symptoms. Mechanism, scavenges free radicals, preventing peroxidation of polyunsaturated fatty acids. Vitamin K, phylloquinone and menaquinone. Functions, coenzyme for gamma-glutamyl carboxylation of clotting factors 2, 7, X, and X. Sources, green leafy vegetables, gut microbiota synthesis. Deficiency, hemorrhagic disorders, easy bruising. Mechanism, essential for post-translational modification of blood coagulation proteins. 2, water-soluble vitamins. These are not stored significantly in the body and require regular dietary intake. They generally function as coenzymes in various metabolic pathways. Vitamin B1, thiamine. Coenzyme form, thiamine pyrophosphate TPP. Functions, carbohydrate metabolism, oxidative decarboxylation of alpha-keto acids. Deficiency, beriberi, Wernicke-Korsakoff syndrome, especially in alcoholism. Enzymes, pyruvate dehydrogenase, alpha-ketoglutarate dehydrogenase, transcriptase. Vitamin B2, riboflavin. Coenzymes, FMN and FAD. Functions, redox reactions in electron transport and oxidative metabolism. Deficiency, angular stomatitis, chylosis, glossitis. Enzymes, succinate dehydrogenase, acyl-CoA dehydrogenase. Vitamin B3, niacin. Coenzymes, NAD+, NADP+. Functions, redox reactions, energy metabolism. Deficiency, pellagra 4Ds, diarrhea, dermatitis, dementia, death. Can be synthesized from tryptophan. Vitamin B5 pantothenic acid. Component of coenzyme A. Functions, acyl group transfer reactions, fatty acid metabolism. Deficiency, rare, may cause fatigue, GI symptoms, paresthesia. Vitamin B6 pyridoxine, pyridoxal, pyridoxamine. Coenzyme, pyridoxal phosphate, PLP. Functions, transamination, decarboxylation, neurotransmitter synthesis. Deficiency, convulsions, peripheral neuropathy. Enzymes, aminotransferases ALT, AST glutamate decarboxylase. Vitamin B7 biotin. Coenzyme for carboxylase enzymes. Functions, fatty acid synthesis, gluconeogenesis. Deficiency, dermatitis, alopecia, caused by raw egg white avidin binds biotin. Vitamin B9 folate. Coenzyme, tetrahydrofolate THF. Functions, 1-carbon transfer in DNA, RNA synthesis. Deficiency, megaloblastic anemia, neural tube defects in fetus. Antagonists, methotrexate inhibits DHFR, blocking THF formation. Vitamin B12 cobalamin. Functions: DNA synthesis, fatty acid and amino acid metabolism. Coenzymes: methylcobalamin, 5'-deoxyadenosylcobalamin. Deficiency: pernicious anemia, neuropathy, methylmalonic acidemia. Needs intrinsic factor for absorption in endothelium. Vitamin C, ascorbic acid. Functions: antioxidant, collagen synthesis, iron absorption. Deficiency: scurvy, bleeding gums, joint pain. Mechanism: cofactor for proline and lysine hydroxylation in collagen synthesis. Role of vitamins in enzyme catalysis. Many vitamins act as precursors for coenzymes and prosthetic groups essential for the catalytic activity of enzymes. Deficiency of these vitamins impairs the function of specific enzymes, which manifests in clinical symptoms and metabolic disorders. Clinical and biotechnological applications: vitamin-based supplementation in metabolic disorders. Diagnostic biomarkers for deficiencies, e.g., methylmalonic acid for B12. Folate antagonists, e.g., methotrexate used in chemotherapy. Vitamin C and antioxidant therapy and wound healing. Previous year questions, PYQs with answers 1. CSIR Net Deck 2013. Which of the following vitamins acts as a coenzyme in carboxylation reactions? Biotin. Beta-thiamine C, riboflavin D, niacin. Answer: a biotin. Biotin is a coenzyme for carboxylases like pyruvate carboxylase and acetyl-CoA carboxylase. 2. CSIR Net June 2015. A deficiency of which vitamin causes megaloblastic anemia? A vitamin B1. B vitamin B9 C, vitamin B6 D, vitamin C. Answer: B vitamin B9. Folate is essential for nucleotide synthesis. Its deficiency leads to impaired DNA replication and anemia. 3. CSIR Net Deck 2018. Which of the following statements is true about vitamin K? A. It is water soluble. B. It is required for DNA synthesis. C. It is required for gamma carboxylation of clotting factors. D. It acts as an antioxidant. Answer: C. It is required for gamma carboxylation of clotting factors. Vitamin K modifies glutamate residues on clotting proteins to allow calcium binding. Let me know when you're ready for the next topic: enzymes, bioenergetics, or any specific area from this unit. You said. Stabilizing interactions. ChatGPT said. Here is your CSIR Net JRF Life Sciences high quality lecture on unit molecules and their interaction relevant to biology topic: stabilizing interactions. For CSIR Net JRF, advanced level with PYQs, no tables, maximum detail. Stabilizing interactions are non-covalent forces that play a critical role in maintaining the structure and function of biological macromolecules, including proteins, nucleic acids, and lipid membranes. While covalent bonds establish the primary structure of macromolecules, it is a network of stabilizing interactions that ensure proper folding, three-dimensional conformation, molecular recognition, and dynamic behavior in the biological environment. These interactions are reversible, non-covalent, and relatively weak individually, but in combination they provide significant structural stability and specificity. Their disruption can lead to denaturation, loss of biological activity, and disease. Understanding these interactions is fundamental to the fields of molecular biology, structural biology, drug design, and enzymology. 1. Hydrogen bonds. Hydrogen bonding is one of the most critical stabilizing interactions in biology. It occurs when a hydrogen atom covalently bonded to a highly electronegative atom, like N or O, forms a weak electrostatic interaction with another electronegative atom. In proteins, stabilize alpha helices and beta sheets in secondary structure. In nucleic acids, responsible for base pairing, N equals T with 2 H bonds, G is defined as C with 3 H bonds, maintaining the double helix. In enzymes and receptors, aid in substrate recognition and transition state stabilization. Though individually weak, 1-5 kilocalories per mole, multiple hydrogen bonds can produce substantial stability and specificity. 2. Ionic interactions, salt bridges. These occur between oppositely charged side chains of amino acids, e.g., lysine and glutamate. Salt bridges combine electrostatic attraction with hydrogen bonding. Role in proteins, commonly found in enzyme active sites and protein-protein interfaces. pH sensitivity. These interactions can be disrupted by changes in pH, affecting protein stability. Salt bridges are important in thermostability of proteins, especially in extremophiles where high temperature environments require enhanced structural rigidity. 3. Hydrophobic interactions. Hydrophobic interactions are entropy-driven forces where nonpolar groups aggregate in aqueous environments to minimize their disruptive effect on water structure. Driving force of protein folding. Nonpolar side chains cluster in the protein core. Membrane formation. Lipid bilayers form due to hydrophobic tails avoiding water. Molecular recognition. Active sites often have hydrophobic patches for ligand binding. Hydrophobic interactions are crucial for tertiary structure and are significantly influenced by temperature and solvent polarity. 4. Van der Waals forces. London dispersion forces. These are transient dipole-induced dipole interactions that occur between all atoms in close proximity. Role in protein packing. Allow tight packing of atoms in the hydrophobic core. Enzyme substrate binding. Ensure snug fit in active sites through shape complementarity. Though individually very weak, 0.5 minus 1 kilocalorie per mole, the cumulative effect of many van der Waals interactions contributes significantly to overall stability. 5. Pi-pi stacking and cation-pi interactions. These interactions occur between aromatic rings or between a cation, like Li+, and an aromatic system, like phenylalanine. In nucleic acids, pi-pi stacking between bases adds to helical stability. In proteins, found in ligand binding sites and protein interfaces. In receptors, important for neurotransmitter recognition, e.g., acetylcholine with aromatic cage in receptor. They play a crucial role in molecular recognition and folding fidelity. 6. Dipole-dipole and dipole-induced dipole interactions. Molecules with permanent dipoles can align in ways that allow favorable interactions. In protein-solvent interactions, help orient polar side chains at the surface. Stabilization of protein folding intermediates through favorable dipole alignments. These interactions are weaker than hydrogen bonds but stronger than van der Waals forces. 7. Water-mediated interactions. Water molecules often mediate interactions between biomolecules by forming bridging hydrogen bonds. In enzyme active sites, water can assist in proton transfer or ligand positioning. In protein interfaces, water bridges enhance specificity in protein-protein recognition. Ignoring solvent effects can lead to misinterpretation of molecular stability and interaction energies. 8. Disulfide bridges technically covalent, but often mentioned in stabilizing context. These are covalent bonds between two cysteine residues forming cysteine. While not a non-covalent interaction, disulfide bonds provide redox-regulated stability to extracellular proteins. Example: immunoglobulins, insulin, and keratin contain disulfide bridges. Breaking and reforming, involved in protein folding pathways. Biological significance. Protein folding, stabilizing interactions guide and maintain the native conformation. Molecular recognition, ensure specificity in ligand binding, enzyme catalysis, and signal transduction. Structural integrity, maintain double helix in DNA, globular conformation in proteins, and bilayer formation in membranes. Evolutionary advantage, organisms have evolved to fine-tune these interactions for optimal function under different conditions, e.g., thermophilic versus mesophilic proteins. Previous year questions, PYQs with answers 1. CSIR Net Deck 2014. Which of the following interactions predominantly contribute to the stability of protein tertiary structure? A. Peptide bonds. B. Disulfide bonds only. C. Hydrophobic interactions. D. Hydrogen bonds only. Answer: C. Hydrophobic interactions. Hydrophobic collapse is a major driving force for tertiary structure formation. 2. CSIR Net June 2019. Which of the following contributes the most to the specificity of interaction between a ligand and a protein receptor? A. Van der Waals forces. B. Hydrophobic effect. C. Hydrogen bonding and electrostatic interactions. D. Covalent bonds. Answer. C. Hydrogen bonding and electrostatic interactions. Specificity is primarily governed by directional interactions like H bonds and ionic forces. 3. CSIR Net Deck 2016. The pi-pi stacking interactions play a major role in stabilizing a tertiary structure of proteins B, alpha helical structure of protein C, base pair stacking in DNA D, disulfide linkage in proteins. Answer. C. Base pair stacking in DNA. Pi-pi interactions between adjacent bases in DNA provide significant structural stability. Let me know when you're ready for the next lecture on enzymes, bioenergetics, or any other CSIR Net life science unit. I'll keep the same quality and format. You said. Van der Waals ChatGPT said. Here is your CSIR Net JRF Life Sciences high quality lecture on unit molecules and their interaction relevant to biology topic. Van der Waals forces. Van der Waals forces are weak, non-covalent interactions that occur between molecules as a result of temporary fluctuations in the electron density of atoms. These interactions are ubiquitous in biological systems and play a crucial role in the structure and behavior of molecules, especially in large macromolecules like proteins, nucleic acids, and lipids. Despite being individually weak, typically in the range of 0.5 - 1 kilocalorie per mole, their cumulative effect contributes significantly to molecular recognition, molecular packing, and the stabilization of biomolecular structures. Van der Waals forces are generally divided into two types. Dispersion forces, London forces. Dipole-dipole interactions. Both of these types are based on electrostatic interactions but differ in the nature of the molecules involved. 1. Dispersion forces, London forces. These are the most common form of van der Waals forces and occur due to instantaneous dipoles that are created when the electron distribution in an atom or molecule becomes temporarily uneven. This transient dipole can induce a dipole in neighboring molecules, resulting in an attraction between them. Nature, temporary or induced dipoles. Importance. These forces are distance dependent, meaning their strength increases as the interacting molecules approach one another. At very short distances, they are repulsive, but at intermediate distances, they become attractive. In biological systems, dispersion forces are important in the packing of hydrophobic molecules in proteins, where nonpolar amino acid side chains aggregate in the protein core to avoid water molecules, contributing to the protein's tertiary structure. 2. Dipole-dipole interactions. These occur between molecules that have permanent dipoles, where there is a partial positive charge on one end and a partial negative charge on the other. The positive end of one molecule is attracted to the negative end of another molecule. In polar molecules, molecules with significant electronegativity differences, such as water, can engage in dipole-dipole interactions. In proteins and nucleic acids, these interactions are crucial for maintaining the secondary structure of proteins, such as in the formation of alpha helices and beta sheets. In DNA, dipole-dipole interactions can assist in the stabilization of base pairing through hydrogen bonds, where the polar nature of nitrogen and oxygen atoms contributes to the specificity of base pairing, e.g., AT, GC. 3. Role of van der Waals forces in protein structure. In proteins, van der Waals forces are essential for the folding and stability of the tertiary structure. While hydrophobic interactions and hydrogen bonds are often emphasized, the role of van der Waals forces cannot be underestimated. Packing of the hydrophobic core. The hydrophobic side chains of amino acids in the protein core are stabilized by van der Waals interactions. These interactions help to minimize the exposure of nonpolar residues to the aqueous environment. Protein-protein interaction. In protein-protein interfaces, van der Waals forces contribute to the tight packing and complementary shape needed for high specificity and binding affinity. Induced fit mechanism. Enzymes often undergo conformational changes upon substrate binding, and van der Waals forces are involved in fine-tuning the enzyme-substrate interaction by facilitating close contact. 4. Van der Waals forces in nucleic acids. Van der Waals interactions play an important role in stabilizing the double helix structure of DNA. While hydrogen bonds between complementary base pairs are crucial for base pairing specificity, pi-pi stacking interactions between the aromatic rings of adjacent bases further stabilize the DNA helix. Base pairing. The interaction of bases through van der Waals forces, along with hydrogen bonds, provides the structural integrity of the double helix. DNA packing. In chromatin, van der Waals interactions contribute to the compaction and folding of DNA, interacting with proteins to form the nucleosome structure. 5. Van der Waals forces in membrane formation. In biological membranes, lipid bilayers are stabilized by hydrophobic interactions, but van der Waals forces also play a crucial role in stabilizing the hydrophobic core of the lipid bilayer. These forces are responsible for lipid packing. Lipid molecules arrange themselves in a bilayer with their hydrophobic tails interacting via van der Waals forces, forming a stable membrane structure. Membrane fluidity. The nature of van der Waals interactions between lipid tails can influence the fluidity and permeability of the membrane. 6. Van der Waals forces in drug design. The understanding of van der Waals interactions is critical in the field of drug design, especially for the development of small molecules that can bind to enzyme active sites or receptors. The affinity of a ligand for a target is often determined by its ability to form van der Waals interactions in addition to hydrogen bonds and electrostatic forces. Ligand binding. Drugs can be designed to interact specifically with the van der Waals surface of a receptor or enzyme, ensuring a high degree of selectivity. Molecular docking. In computational drug design, van der Waals interactions are an essential part of the algorithms used to predict how small molecules bind to their targets. Previous year questions PYQs with answers 1. CSIR Net Deck 2012. Which of the interactions is most responsible for the stabilizing of protein tertiary structure? A. Ionic bonds. B. Hydrogen bonds. C. Van der Waals interactions. D. Covalent bonds. Answer. C. Van der Waals interactions. Van der Waals interactions, together with hydrophobic interactions, contribute to the packing and stability of protein tertiary structure. 2. CSIR Net June 2014. In a DNA molecule, which of the following interactions plays a role in stabilizing the double helix? A. Hydrophobic interactions between phosphate groups. B. Pi-pi stacking between adjacent purine and pyrimidine bases. C. Covalent bonds between sugar and phosphate groups. D. Ionic interactions between complementary base pairs. Answer. B. Pi-pi stacking between adjacent purine and pyrimidine bases. Pi-pi stacking interactions are van der Waals forces between the aromatic rings of adjacent nitrogenous bases in DNA. 3. CSIR Net Deck 2017. Which of the following statements regarding van der Waals forces is false? A. They are strong at very close distances. B. They are involved in molecular recognition. C. They increase in strength with the size of the molecules involved. D. They are electrostatic interactions between permanent dipoles. Answer. D. They are electrostatic interactions between permanent dipoles. Van der Waals forces include both temporary dipoles, London dispersion, and permanent dipoles, dipole-dipole interactions, but they are generally weak in short-range interactions. Let me know if you need further elaboration or the next lecture on enzyme mechanisms, bioenergetics, or any other topic from CSIR Net Life Sciences. You said. Electrostatic. ChatGPT said. Here is your CSIR Net JRF Life Sciences high-quality lecture on unit molecules and their interaction relevant to biology topic. Electrostatic interactions. Electrostatic interactions, also known as ionic interactions, are one of the fundamental types of non-covalent forces in biological systems. These interactions occur due to the attraction between oppositely charged ions or the repulsion between like charged ions. They are much stronger than van der Waals forces but weaker than covalent bonds. In biological molecules, electrostatic interactions are pivotal for maintaining structural integrity, facilitating molecular recognition, and enabling many biochemical processes such as enzyme catalysis, DNA-protein interactions, and signal transduction. 1. Nature of electrostatic interactions. Electrostatic interactions are the forces between charged entities, either atoms, ions, or groups of molecules, that result from their electric fields. The strength of these interactions depends on the magnitude of the charges and the distance between them. The Coulomb's law mathematically describes the force between two charges. F equals K dot operator divides Q1 dot operator Q2 divides R2 F equals R2. K dot operator divides Q1. Dot operator Q2 divides. Where F is the force between the charges. K is Coulomb's constant. Q1 and Q2 are the magnitudes of the two charges. R is the distance between the charges. This relationship indicates that electrostatic force is stronger at shorter distances and stronger with higher charges. 2. Role in protein structure and function. Electrostatic interactions are critical for the structure and stability of proteins. They are involved in the folding of proteins, their tertiary structure, and interactions with other molecules. These interactions often occur between charged side chains of amino acids, e.g., lysine, arginine, glutamic acid, and aspartic acid. Salt bridges, formed by the attraction between oppositely charged residues, e.g., between lysine and glutamate. These interactions can stabilize protein structures and help maintain active sites in enzymes. Protein-protein interactions. Electrostatic interactions are key for molecular recognition during enzyme-substrate binding or protein complex formation. They ensure high specificity and stability in protein complexes. 3. Electrostatic interactions in nucleic acids. In DNA and RNA, electrostatic interactions between the phosphate groups of the sugar phosphate backbone and positively charged ions, such as Mg squared, not help to stabilize the double helix and facilitate various processes such as DNA packaging, transcription, and replication. DNA packaging. The negatively charged phosphate groups of DNA interact with positively charged histone proteins, leading to the formation of nucleosomes in chromatin. DNA-protein interactions. Electrostatic interactions between charged residues in histones and DNA enable the binding of transcription factors to DNA during processes like gene expression regulation. Ionic conditions. The stability of the DNA helix is influenced by the ionic strength of the environment, where higher salt concentrations can stabilize the double helix by neutralizing repulsive charges on the backbone. 4. Electrostatic interactions in enzyme catalysis. In enzyme catalysis, electrostatic interactions are essential for the binding of substrates and the formation of transition states. These interactions contribute to the induced fit model of enzyme function, where the enzyme's active site undergoes conformational changes upon substrate binding. Enzyme-substrate binding. Electrostatic interactions between the active site and the substrate can orient the substrate in a specific way that promotes catalysis. Charge stabilization. Enzymes may stabilize charge transition states during catalysis by interacting with charged residues in the active site. Cofactors. Many enzymes use metal ions, e.g., Mg squared, Zn squared, that coordinate with charged amino acid side chains, aiding in catalysis by stabilizing negative charges on substrates or transition states. 5. Electrostatic interactions in membrane biology. In cell membranes, electrostatic interactions are essential for the stabilization of lipid bilayers and the function of membrane proteins. Lipid bilayers. The hydrophilic phosphate heads of phospholipids interact electrostatically with water molecules, while hydrophobic tails face inward, forming a stable bilayer structure. Membrane proteins. Electrostatic interactions between membrane proteins and the lipid bilayer, as well as between different membrane proteins, regulate processes like signal transduction, ion transport, and cell communication. 6. Electrostatic interactions in drug design. In drug design, electrostatic complementarity is crucial for designing high-affinity drugs that interact specifically with their target molecules, whether enzymes, receptors, or other biomolecules. Ligand receptor binding. The strength and specificity of ligand receptor interactions are often governed by electrostatic forces between the ligand and the receptor's charged regions. Pharmacophore design. Electrostatic interactions are a key feature of the pharmacophore, the minimal structure required for a molecule to be active in the target receptor site. 7. Electrostatic interactions in molecular dynamics. In molecular dynamics simulations, the electrostatic potential of a system is essential for understanding the behavior of biomolecules. These simulations allow the prediction of how charged particles interact within biological systems, including protein folding, ligand binding, and protein-protein docking. Previous year questions PYQs with answers 1. CSIR Net Deck 2013. Which of the following interactions contributes to the stability of the alpha helix in proteins? Electrostatic interactions between side chains B. Hydrophobic interactions between nonpolar side chains C. Hydrogen bonding between the backbone atoms D. Van der Waals interactions between side chains answer C. Hydrogen bonding between the backbone atoms. Hydrogen bonds stabilize the alpha helix structure in proteins. 2. CSIR Net June 2015. In DNA, which of the following is true about electrostatic interactions? A. They contribute to the formation of the double helix by neutralizing charges on the DNA backbone. B. They are relevant to DNA structure. C. They help in the stabilization of base pairs. D. They are mainly involved in hydrogen bonding between the base pairs. Answer. A. They contribute to the formation of the double helix by neutralizing charges on the DNA backbone. The electrostatic interactions between the phosphate groups and positively charged ions help stabilize the double helix structure of DNA. 3. CSIR Net Deck 2018. The ionic interactions in proteins are primarily responsible for The ionic interactions in proteins are primarily responsible for a peptide bond formation. B. Protein folding. C. Hydrogen bonding between peptide groups D. Stabilizing the quaternary structure answer B. Protein folding. Electrostatic interactions play a crucial role in stabilizing protein folding and contributing to tertiary structure. This concludes the lecture on electrostatic interactions. Let me know when you're ready for the next topic or need further clarification. You said, hydrogen bonding ChatGPT said. Here is your CSIR Net JRF Life Sciences high quality lecture on Unit, Molecules and their interaction relevant to biology topic, hydrogen bonding. Hydrogen bonding is a type of electrostatic interaction that occurs when a hydrogen atom covalently bonded to an electronegative atom, like oxygen, nitrogen, or fluorine, is in close proximity to another electronegative atom with a lone pair of electrons. This interaction is significantly weaker than a covalent bond but plays a critical role in the stability and function of many biomolecules. Hydrogen bonds are key players in various biological processes, including the structure of DNA, protein folding, enzyme-substrate interactions, and the solubility of compounds in water. The directionality and strength of hydrogen bonds make them highly effective in promoting molecular recognition and maintaining macromolecular stability. 1. Nature of hydrogen bonding. A hydrogen bond is formed when hydrogen is covalently bonded to a highly electronegative atom, commonly oxygen or nitrogen. This hydrogen is attracted to a lone pair of electrons on another electronegative atom. The strength of a hydrogen bond is typically in the range of 1 to 5 kcal per mole, much weaker than a covalent bond, approximately 50 to 100 kcal per mole. Despite their relative weakness, hydrogen bonds are highly significant in biological systems due to their directionality and specificity. There are two main types of hydrogen bonds. Intermolecular hydrogen bonds. These occur within the same molecule. Intermolecular hydrogen bonds. These occur between different molecules. 2. Role of hydrogen bonding in protein structure. In proteins, hydrogen bonds play a critical role in the formation and stabilization of their secondary and tertiary structures. These bonds are primarily responsible for maintaining the shape and function of proteins by stabilizing alpha helices, beta sheets, and protein folding. Alpha helix. Hydrogen bonds form between the cardinal oxygen of one amino acid and the amide hydrogen of another amino acid 4 residues away in the polypeptide chain. This stabilizes the helical structure. Beta sheet. Hydrogen bonds form between backbone amide groups of different polypeptide strands, stabilizing the sheet-like structure. Tertiary structure. Hydrogen bonds contribute to the folding of the protein into its functional three-dimensional shape by stabilizing interactions between different parts of the protein. 3. Hydrogen bonding in nucleic acids. In DNA, hydrogen bonds are responsible for the specific pairing of base pairs. The base pairing follows Chargaff's rule, where adenine A pairs with thymine T through 2 hydrogen bonds. Cytosine C pairs with guanine G through 3 hydrogen bonds. The formation of these hydrogen bonds between complementary bases in 2 strands of DNA stabilizes the double helix structure. The hydrogen bonds ensure the specificity and accuracy of DNA replication and transcription processes. DNA replication. Hydrogen bonds between the base pairs are broken by enzymes during DNA replication, allowing the complementary strands to separate and new strands to be synthesized. RNA structure. In RNA, hydrogen bonds also help stabilize the secondary and tertiary structures of the molecule, particularly in the formation of stem loops and other structural motifs. 4. Hydrogen bonding in water. Water is often referred to as a solvent of life due to its ability to form extensive hydrogen bonds. These interactions confer many of water's unique properties, such as its high boiling point, high specific heat, and high surface tension. These properties are crucial for biological systems. High specific heat. Water can absorb a lot of heat before its temperature rises, which helps maintain homeostasis in living organisms. Solubility of biomolecules. Water's hydrogen bonding enables it to dissolve many polar and ionic compounds, facilitating the transportation and interaction of biomolecules in cells and tissues. Surface tension. The hydrogen bonds between water molecules create surface tension, which is important in processes like capillary action and the formation of cellular structures. 5. Hydrogen bonding and enzyme-substrate interaction. Hydrogen bonds are key to enzyme-substrate binding. The active site of an enzyme forms hydrogen bonds with the substrate, which helps in the proper orientation of the substrate for catalysis. These interactions also contribute to the induced fit mechanism, where the enzyme undergoes a conformational change upon binding to the substrate, optimizing the catalytic process. Specificity. The enzyme's active site contains specific hydrogen bond donors and acceptors that match the functional groups of the substrate, ensuring high specificity. Stabilization of transition states. Hydrogen bonding can stabilize the transition state of a reaction, lowering the activation energy and enhancing the enzyme's catalytic efficiency. 6. Hydrogen bonding in drug design. In pharmacology, hydrogen bonding plays a crucial role in drug design, particularly in the binding of ligands to receptors or enzymes. Drugs are designed to form optimal hydrogen bonds with the target molecule, improving binding affinity and selectivity. Pharmacophore. The functional groups of a drug molecule that participate in hydrogen bonding with the target receptor form part of the pharmacophore. Hydrogen bond acceptors and donors. A drug molecule can be optimized by adjusting its structure to increase the number of potential hydrogen bond donors and acceptors, enhancing binding to the receptor. 7. Hydrogen bonding and other biological processes. Protein-ligand interactions. The binding of ligands to proteins, such as in signal transduction, often involves hydrogen bonds that stabilize the binding. Antibody-antigen interactions. The specificity of the antibody-antigen interaction is also influenced by hydrogen bonds, which contribute to the tight binding and recognition of antigens by antibodies. Cell signaling. Hydrogen bonding in molecules like G-protein coupled receptors, GPCRs, and kinesis helps propagate cellular signals. Previous year questions PYQs with answers 1. CSIR Net December 2015. Which of the following interactions is primarily responsible for the base pairing in DNA? A. Ionic interactions. B. Hydrogen bonds. C. Covalent bonds. D. Hydrophobic interactions. Answer. B. Hydrogen bonds. Hydrogen bonds between base pairs in the DNA double helix stabilize the structure and contribute to specificity during replication. 2. CSIR Net June 2017. Hydrogen bonds are important in stabilizing the secondary structure of proteins. Which of the following is true regarding the role of hydrogen bonds in proteins? A. They form between the side chains of amino acids. B. They stabilize the alpha helix and beta sheet structures. C. They contribute to the formation of peptide bonds. D. They hold the tertiary structure of proteins intact. Answer. B. They stabilize the alpha helix and beta sheet structures. Hydrogen bonds form between the backbone amide groups in proteins, stabilizing the alpha helix and beta sheet secondary structures. 3. CSIR Net Deck 2018. The specificity of the double helix formation of DNA is mainly due to a. Hydrophobic interactions between the base pairs. B. Hydrogen bonding between complementary bases. C. Covalent bonds between the sugar phosphate backbones. D. Electrostatic interactions between the strands. Answer. B. Hydrogen bonding between complementary bases. Hydrogen bonds between adenine, thymine, and guanine cytosine base pairs ensure the specificity and stability of the DNA double helix. This concludes the lecture on hydrogen bonding. Let me know when you're ready for the next topic or need further clarification. You said hydrophobic interaction. ChatGPT said. Here is your CSIR Net JRF Life Sciences high quality lecture on Unit Molecules and their interaction relevant to biology topic. Hydrophobic interactions. Hydrophobic interactions refer to the tendency of nonpolar molecules or parts of molecules to aggregate in aqueous solutions away from the water molecules. This phenomenon occurs due to the inability of nonpolar substances to form favorable interactions with water molecules, which are highly polar. While not a traditional chemical bond, hydrophobic interactions play a crucial role in shaping the structure and function of many biological macromolecules, including proteins, lipids, and nucleic acids. 1. Nature of hydrophobic interactions. Hydrophobic interactions arise from the unfavorable enthalpy change that occurs when nonpolar molecules are exposed to water. Water molecules surround hydrophobic nonpolar molecules and disrupt the hydrogen bonding network that exists in bulk water, leading to a decrease in the system's entropy. To minimize this energetic cost, nonpolar molecules tend to aggregate together, reducing their surface area exposed to water and maximizing the water molecule's hydrogen bonding network. This aggregation leads to an increase in the entropy of the surrounding water, making the system more thermodynamically stable. Unlike covalent or ionic interactions, hydrophobic interactions are entropic in nature and are driven by the increase in disorder in the surrounding solvent, rather than direct attractive forces between the molecules themselves. 2. Hydrophobic effect in protein folding. The hydrophobic effect plays a central role in the folding of proteins into their native three-dimensional structures. Nonpolar amino acid residues, such as valine, leucine, and phenylalanine tend to cluster in the interior of the protein, away from the aqueous environment. This inward folding of hydrophobic residues is driven by the need to minimize exposure to water and is crucial for the formation of a stable, functional protein. Protein folding. The hydrophobic effect contributes to the formation of tertiary structure by driving the protein to fold in a way that exposes polar residues to the solvent and buries nonpolar residues in the interior. Protein misfolding. If hydrophobic residues are exposed to the aqueous environment, this can result in misfolding and aggregation, contributing to diseases such as Alzheimer's disease and Parkinson's disease. 3. Hydrophobic interactions in membrane formation. In biological membranes, the hydrophobic effect is responsible for the formation of lipid bilayers, which are the fundamental structure of cell membranes. The hydrophobic tails of phospholipids face each other in the interior of the membrane, while the hydrophilic heads are oriented towards the aqueous environment on both sides of the membrane. Lipid bilayers. The hydrophobic interactions between the nonpolar fatty acid tails drive the self-assembly of the lipid bilayer structure, which acts as a selective barrier to the movement of ions and molecules. Membrane proteins. Membrane proteins that span the lipid bilayer typically have hydrophobic regions that interact with the lipid tails and hydrophilic regions that interact with the aqueous environment inside and outside the cell. The integrity of the cell membrane is thus largely maintained by hydrophobic interactions, allowing cells to compartmentalize their internal environments and regulate substance exchange. 4. Hydrophobic interactions in nucleic acids. Hydrophobic interactions also play a role in the stabilization of nucleic acid structures. In the double helix of DNA, the hydrophobic bases are stacked inside the helix, away from the aqueous environment. This base stacking interaction, driven by hydrophobic forces, contributes to the overall stability of the DNA molecule. Base stacking in DNA. The hydrophobic effect between the aromatic rings of the purine and pyrimidine bases in DNA stabilizes the double helix by creating attractive forces that contribute to the overall helical structure. RNA structure. Similarly, hydrophobic interactions play a role in the secondary and tertiary structure of RNA, where nonpolar residues are buried within the molecule to avoid contact with water. 5. Hydrophobic interactions in ligand binding. Hydrophobic interactions are essential in ligand binding to receptors or enzymes. Many drug molecules and natural ligands bind to their targets through hydrophobic interactions, where the nonpolar regions of the ligand interact with nonpolar areas of the receptor or enzyme. Receptor ligand binding. The binding of nonpolar ligands to hydrophobic pockets in the receptor protein is often facilitated by hydrophobic interactions. This is particularly important in processes such as signal transduction and enzyme catalysis. Pharmacology. Drug molecules that are hydrophobic often have a higher affinity for their targets because they can effectively interact with hydrophobic sites on the receptor or enzyme. This characteristic is key in the development of many hydrophobic drug molecules. 6. Hydrophobic interactions in protein-protein interactions. Hydrophobic interactions also play a critical role in protein-protein interactions. When proteins interact with each other, hydrophobic residues often cluster together in the interface between the proteins, while polar residues are pushed to the exterior. Protein complex formation. Hydrophobic interactions contribute to the specificity and affinity between interacting proteins, and this is often observed in processes like protein-protein docking or enzyme substrate binding. Membrane protein complexes. In membrane proteins, hydrophobic interactions between proteins and lipids help maintain the stability and functionality of membrane-bound protein complexes. 7. Hydrophobic interactions in drug design. In drug design, understanding hydrophobic interactions is crucial for designing molecules with optimal binding properties. Drugs are often engineered to fit into hydrophobic pockets of target proteins, maximizing the hydrophobic surface area exposed to the ligand. Molecular docking. The success of many drugs depends on the ability of the molecule to interact with hydrophobic residues in the active site of the target enzyme or receptor. Thus, the hydrophobic effect is key in developing effective therapeutic agents. Hydrophobicity and bioavailability. Hydrophobic drugs are often designed to be lipophilic, allowing them to pass through cell membranes and reach their target sites effectively. 8. Hydrophobic interactions in biological systems. Protein aggregation and diseases. The failure of hydrophobic interactions in protein folding and stability can lead to protein aggregation, which is a hallmark of many neurodegenerative diseases like Huntington's disease, Alzheimer's disease, and Parkinson's disease. Chaperones. Molecular chaperones help refold misfolded proteins, preventing unwanted hydrophobic interactions that could lead to aggregation. Previous year questions PYQs with answers 1. CSIR Net December 2015. Which of the following interactions is primarily responsible for the stabilization of the protein's tertiary structure? A. Hydrogen bonds. B. Ionic bonds. C. Hydrophobic interactions. D. Disulfide bonds. Answer. C. Hydrophobic interactions. Hydrophobic interactions between nonpolar residues help stabilize the tertiary structure by driving them into the interior of the protein. 2. CSIR Net June 2017. Which of the following biomolecular interactions is responsible for the self-assembly of the lipid bilayer in biological membranes? A. Hydrophilic interactions. B. Hydrophobic interactions. C. Ionic bonds. D. Van der Waals interactions. Answer. B. Hydrophobic interactions. The hydrophobic effect causes the nonpolar lipid tails to aggregate together, forming the core of the lipid bilayer. 3. CSIR Net Deck 2018. Hydrophobic interactions in proteins primarily contribute to which of the following? A. Primary structure. B. Secondary structure. C. Tertiary structure. D. Quaternary structure. Answer. C. Tertiary structure. Hydrophobic interactions are primarily responsible for the folding and stabilization of the protein's tertiary structure. This concludes the lecture on hydrophobic interactions. Let me know when you're ready for the next topic or need further clarification. You said. Principles of biophysical chemistry. ChatGPT said. Here is your CSIR Net JRF Life Sciences High Quality Lecture on Unit. Principles of biophysical chemistry. Introduction to biophysical chemistry. Biophysical chemistry is the branch of chemistry that applies the principles of physics and chemistry to understand the structure, function, and interaction of biological macromolecules, such as proteins, nucleic acids, lipids, and carbohydrates. This field bridges the gap between biology and chemistry by providing tools and techniques to study the molecular properties and behaviors of biological molecules. Biophysical chemistry focuses on understanding the thermodynamics, kinetics, and structural characteristics of biological systems, as well as the interactions that dictate molecular behavior. Techniques used in biophysical chemistry include spectroscopy, calorimetry, and chromatography, among others, which help characterize molecular interactions, determine the structure of biomolecules, and study their behavior in various environments. 1. Thermodynamics in biophysical chemistry. Thermodynamics is fundamental to understanding the behavior of biological systems. In biophysical chemistry, thermodynamics describes the flow of energy and the changes in the entropy and enthalpy of a system. The primary concepts include free energy delta G. The Gibbs free energy change delta G determines the spontaneity of a process. In biochemical reactions, a negative delta G indicates that the process is thermodynamically favorable and can proceed spontaneously, while a positive delta G implies that the process requires energy input. Delta G equals delta H minus T delta S. Delta G equals delta H minus T delta S where delta H. Delta H equals change in enthalpy heat content. T. T equals temperature in Kelvin. Delta S. Delta S equals change in entropy degree of disorder. Enthalpy delta H, the total heat content of the system, which indicates whether a reaction is exothermic, releases heat, or endothermic, absorbs heat. Entropy delta S, the measure of the disorder or randomness in the system. A positive change in entropy favors the spontaneity of a process. Equilibrium constant K. The equilibrium constant K describes the balance between reactants and products in a reversible reaction and is related to the free energy change by the equation. Delta G equals minus RT lane K. Delta G equals minus RT ln K where R equals universal gas constant. T equals temperature in Kelvin. K equals equilibrium constant. 2. Kinetics in biophysical chemistry. Kinetics in biophysical chemistry studies the rates of biochemical reactions and the factors that influence these rates. It involves the measurement of reaction velocity and understanding the mechanisms by which reactions occur. Reaction rate V. The rate of a reaction can be defined as the change in concentration of reactants or products over time. It is often expressed in terms of the rate constant K in the equation. V equals KAN versus equals KAN. Where V equals reaction rate. K equals rate constant. A equals concentration of reactant. N equals order of reaction. Michaelis-Menten kinetics. In enzymatic reactions, the reaction rate is influenced by the concentration of the enzyme and substrate. The Michaelis-Menten equation describes the kinetics of many enzymes. V equals V max S Km plus S versus equals Km plus S V max S where V max equals maximum reaction velocity. S equals substrate concentration. Km equals Michaelis constant substrate concentration at half V max V max. Activation energy A. The activation energy is the energy required to initiate a chemical reaction. In biophysical chemistry, activation energy is important in understanding the efficiency of enzymes and catalysts in lowering the energy barrier for biochemical reactions. 3. Spectroscopic techniques. Spectroscopic techniques are used to study the structure and dynamics of biological molecules. These methods involve the interaction of electromagnetic radiation with matter, providing information about the molecular composition, structure, and dynamics. UV visible spectroscopy. This technique measures the absorbance of ultraviolet or visible light by molecules, typically used to study the absorption spectra of nucleic acids and proteins. It can provide information about the concentration of molecules in solution. Circular dichroism (CD). Circular dichroism spectroscopy is used to study the secondary structure of proteins and nucleic acids. It measures the difference in the absorption of left and right circularly polarized light by chiral molecules, allowing for the determination of alpha helical and beta sheet content in proteins. Fluorescence spectroscopy. This technique measures the emission of light by molecule after it absorbs light at a specific wavelength. It is widely used to study protein folding, ligand binding, and molecular interactions by labeling specific parts of molecules with fluorescent probes. Nuclear magnetic resonance (NMR). NMR spectroscopy is used to determine the three-dimensional structure of proteins, nucleic acids, and other biomolecules in solution. It provides detailed information about the chemical environment of atoms in a molecule. X-ray crystallography. This is the most powerful technique for determining the atomic level structure of proteins and nucleic acids. X-ray diffraction patterns are analyzed to create high-resolution 3D models of macromolecules. 4. Calorimetry. Calorimetry is the measurement of heat changes in biological processes, particularly useful in studying the thermodynamics of molecular interactions. Differential scanning calorimetry (DSC). DSC measures the heat required to increase the temperature of a sample and is used to study protein unfolding and ligand binding. It can provide information about melting temperatures, enthalpic changes, and enthalpy entropy compensation in biomolecular processes. Isothermal titration calorimetry (ITC). ITC measures the heat change during the binding of two molecules, providing detailed information on binding affinity, stoichiometry, and thermodynamic parameters such as enthalpy and entropy changes in molecular interactions. 5. Chromatographic techniques. Chromatography is a technique used to separate and analyze different components of a mixture, including proteins, lipids, nucleic acids, and small molecules. Common chromatographic methods include high-performance liquid chromatography (HPLC). HPLC is used to separate, identify, and quantify biomolecules in complex mixtures. It is commonly used for protein purification, analysis of small molecules, and separation of nucleic acid fragments. Gas chromatography (GC). This method is used to analyze volatile compounds. It is often coupled with mass spectrometry (MS) for detailed analysis. Affinity chromatography. This technique uses specific ligand-receptor interactions to purify biomolecules, such as proteins or nucleic acids, based on their affinity for a specific ligand. 6. Molecular modeling and computational methods. Computational techniques in molecular modeling allow the prediction and visualization of the structure and dynamics of biological molecules. Techniques such as molecular dynamic simulations help understand protein folding, ligand binding, and the conformational changes in biomolecules over time. Previous year questions (PYQs) with answers 1. CSIR Net December 2015. Which of the following spectroscopic techniques is most suitable for determining the secondary structure of proteins? A. UV visible spectroscopy. B. Nuclear magnetic resonance (NMR). C. Circular dichroism (CDT). Fluorescence spectroscopy. Answer. C. Circular dichroism (CD). CD spectroscopy provides information about secondary structure elements such as alpha helices and beta sheets in proteins. 2. CSIR Net June 2017. The activation energy of a biochemical reaction is the energy required to a. Initiate the reaction. B. Form the intermediate complex. C. Achieve the equilibrium state. D. Break the bond between reactants. Answer. A. Initiate the reaction. Activation energy is the minimum energy required for the reactants to undergo a chemical transformation. 3. CSIR Net Deck 2018. Which of the following techniques is primarily used to determine the three-dimensional structure of proteins? A. Fluorescence spectroscopy. B. X-ray crystallography. C. High-performance liquid chromatography (HPLC). D. Mass spectrometry. Answer. B. X-ray crystallography. X-ray crystallography is a gold standard for determining the high-resolution three-dimensional structures of proteins. This concludes the lecture on principles of biophysical chemistry. Let me know when you're ready for the next topic or need further clarification. You said, pH. ChatGPT said. Here is your CSIR Net JRF Life Sciences high-quality lecture on Unit, pH, buffers, and biological significance. Introduction to pH. The term pH refers to the potential of hydrogen and is a measure of the acidity or alkalinity of a solution. It is calculated. The term pH refers to the potential of hydrogen and is a measure of the acidity or alkalinity of a solution. It is calculated as a negative logarithm of the hydrogen. Unit, pH, buffers, and biological significance. Introduction to pH. The term pH refers to the potential of hydrogen and is a measure of the acidity or alkalinity of a solution. It is calculated as a negative logarithm of the hydrogen ion concentration. H plus H plus. In a solution. pH equals minus log H plus. pH equals minus log H plus. A pH of 7 is considered neutral, indicating equal concentrations of hydrogen ions. H plus H plus. And hydroxide ions. OH minus O minus. A pH lower than 7 indicates an acidic solution. More. H plus H plus. Ions than. OH minus O minus. A pH greater than 7 indicates H plus H plus. Ions than. OH minus O minus. A pH greater than 7 indicates an alkaline or basic solution. More. OH minus O minus. Ions than. H plus H plus. For biological systems, pH is an essential factor in determining the structural and functional properties of biomolecules, such as proteins and enzymes, which are often pH sensitive. The role of pH in biological systems. In biological systems, the pH plays a critical role in maintaining the structure and function of biomolecules, ensuring proper enzyme activity and metabolic function. Protein structure. The tertiary and quaternary structures of proteins are highly dependent on ionic interactions and hydrogen bonds, both of which are influenced by pH. For example, changes in pH can disrupt ionic bonds, leading to protein denaturation or alteration of the active site, affecting enzymatic activity. Enzyme activity. Enzymes exhibit optimal activity at specific pH values. For example, pepsin, an enzyme found in the stomach, functions best at a highly acidic pH of around 2, while alkaline phosphatase is most active in basic conditions around pH 9 to 10. Metabolic pathways. Many cellular metabolic pathways involve pH-sensitive reactions. For example, glycolysis in the citric acid cycle can be disrupted if the pH deviates significantly from the physiological range, approximately 7.4. Ionization of biomolecules. The ionization state of biomolecules, e.g., amino acids, nucleotides, is influenced by pH. The ionization of functional groups in amino acids, such as carboxyl groups and amine groups, affects their charge and, consequently, the protein folding and interaction properties. Buffers and their biological significance. A buffer is a solution that resists changes in pH when an acid or base is added. Buffers play a crucial role in maintaining pH stability in biological systems, ensuring that cellular processes occur within an optimal pH range. Buffer capacity. The ability of a buffer to resist changes in pH depends on the concentration of the buffer components and the pKa, acid dissociation constant, of the acid-base pair used. Henderson-Hasselbalch equation. The relationship between the pH of a buffer solution, the pKa of the acid, and the concentration of the acid, HA, Ha and its conjugate base, A minus A minus, is given by the Henderson-Hasselbalch equation. pH equals pKa plus log A minus HA. pH equals pKa plus log Ha, A minus, where pKa is the pH at which the acid is 50% dissociated. A minus A minus is the concentration of the conjugate base, the ionized form. HA. Ha is the concentration of the acid, the undissociated form. This equation helps predict the pH of a solution based on the concentrations of the acid and its conjugate base. Biological buffers. In living organisms, several buffer systems help maintain pH within a narrow range, critical for optimal cellular function. The most important biological buffers include bicarbonate buffer system. This is the primary buffering system in human blood and extracellular fluid. The system consists of carbonic acid HCO and bicarbonate ions HCO. The bicarbonate buffer operates in the lungs and kidneys to maintain the blood pH at around 7.4. Reaction. CO gas plus. HO rightwards harpoon over leftwards harpoon. HCO rightwards harpoon over leftwards harpoon. H++. HCO minus. CO gas plus HO rightwards harpoon over leftwards harpoon HCOH plus. Plus HCO minus. The equilibrium between carbon dioxide, carbonic acid, and bicarbonate helps buffer the pH in the blood. Phosphate buffer system. The phosphate buffer system operates inside cells and in the kidneys. It is similar to the bicarbonate buffer but involves phosphoric acid HPO and its conjugate base HPO and HPO squared. The phosphate buffer is effective in the intracellular environment, where the concentration of phosphates is relatively high. Protein buffering. Proteins can also act as buffers due to the presence of amino groups NH and carboxyl groups COOH, which can gain or lose protons depending on the pH. Histidine residues in proteins are especially significant for buffering because they have a pKa near physiological pH around 7.4. Hemoglobin is a buffer. Hemoglobin in red blood cells acts as a buffer, helping to regulate pH in the blood by binding to protons H, especially during co-transport from tissues to the lungs. pH and disease. Changes in the pH of biological fluids can indicate or contribute to several health conditions. Acidosis, a condition in which the blood pH drops below 7.35. It can occur due to respiratory acidosis, increased CO, or metabolic acidosis, increased acid production or decreased bicarbonate. Alkalosis, a condition in which the blood pH rises above 7.45. It can occur due to respiratory alkalosis, decreased CO levels, or metabolic alkalosis, excessive loss of acid. Previous year questions PYQs with answers 1. CSIR Net Deck 2017. Which of the following is the most important buffer system in human blood? A. Phosphate buffer system. B. Bicarbonate buffer system. C. Protein buffer system. D. Ammonium buffer system. Answer. B. Bicarbonate buffer system. The bicarbonate buffer system helps maintain the pH of the blood within the physiological range of 7.35 to 7.45. 2. CSIR Net June 2019. What is the role of the Henderson-Hasselbalch equation in biological systems? A. It calculates the pH of weak acid solutions. B. It describes the relationship between pH and the concentration of buffer components. C. It measures the pH of protein solutions. D. It helps in understanding protein folding. Answer. B. It describes the relationship between pH and the concentration of buffer components. The Henderson-Hasselbalch equation helps predict the pH of a buffer solution by relating it to the concentrations of acid and its conjugate base. 3. CSIR Net Deck 2020. Which of the following is true for the phosphate buffer system in humans? A. It is the primary buffer in the blood. B. It operates predominantly in the kidney and intracellular fluid. C. It maintains the previous year questions PYQs with answers 1. CSIR Net Deck 2017. Which of the following is the most important buffer system in human blood? A. Phosphate buffer system. B. Bicarbonate buffer system. C. Protein buffer system. D. Ammonium buffer system. Answer. B. Bicarbonate buffer system. The bicarbonate buffer system helps maintain the pH of the blood within the physiological range of 7.35 to 7.45. 2. CSIR Net June 2019. What is the role of the Henderson-Hasselbalch equation in biological systems? A. It calculates the pH of weak acid solutions. B. It describes the relationship between pH and the concentration of buffer components. C. It measures the pH of protein solutions. D. It helps in understanding protein folding. Answer. B. It describes the relationship between pH and the concentration of buffer components. The Henderson-Hasselbalch equation helps predict the pH of a buffer solution by relating it to the concentrations of acid and its conjugate base. 3. CSIR Net Deck 2020. Which of the following is true for the phosphate buffer system in humans? A. It is the primary buffer in the blood. B. It operates predominantly in the kidney and intracellular fluid. C. It maintains the pH of the stomach. D. It operates only in the digestive tract. Answer. B. It operates predominantly in the kidney and intracellular fluid. The phosphate buffer system is most effective inside cells in the kidneys, where phosphate concentrations are high. This concludes the lecture on pH, buffers, and biological significance. Let me know when you're ready for the next topic or need further clarification. You said, buffer, ChatGPT said. Here is your CSIR Net JRF Life Sciences high-quality lecture on Unit, Buffers in Biological Systems Introduction to Buffers. A buffer is a solution that resists changes in pH when small amounts of an acid or a base are added. Buffers are critical in maintaining the pH stability of biological systems, ensuring that enzymatic reactions and cellular processes occur within optimal pH ranges. The buffer capacity is determined by the amount of acid or base the buffer can absorb without causing a significant change in pH. Buffers are composed of weak acids and their conjugate base or weak bases and their conjugate acid. These buffer systems are especially important in maintaining the proper pH of intracellular environments, extracellular fluids, and blood. The mechanism of buffers. A buffer works based on the equilibrium between an acid and its conjugate base. The buffer can neutralize added acids or bases due to this equilibrium. When an acid H is added to a buffer, the conjugate base of the buffer will accept the proton H, forming more of the weak acid form, thereby minimizing the increase in hydrogen ion concentration and thus preventing a drastic drop in pH. When a base O is added to a buffer, the weak acid will donate a proton H to neutralize the hydroxide ions O, forming more of the conjugate base, thus preventing a significant increase in pH. Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is used to relate the pH of a buffer solution to the pKa acid dissociation constant of the weak acid in the